right, so the We Share Solar webpage mentioned earlier that has a curriculum. This is the international deployment curriculum, so it might look a tad bit different, but I think overall they have roughly the same material. So down here in part 4, understanding DC electricity in the solar suitcase, it's a big idea to understand that this is direct current. When you go to test the suitcase and use the suitcase outside and do data collection, if you're in AC, you're not going to get the right data. So this is all about direct current. I am currently in middle school, high school presentation for the DC electricity for solar. So what I did was they had a slideshow. I liked most of the slideshow. Theirs is 38 slides. I made a copy of it and mine is 36 slides. So I made some different additions to my slideshow. Some of the big things that I would like to point out from this is if you choose to talk about this, don't be afraid that you might not fully understand the waterfall analogy. I think it's still super helpful to talk about that. If you need the speaker notes, I think that would be especially helpful. But there's a demonstration you can do with the kids in person. So when we get to that slide, I'll tell you what items you need. The first few slides go over what is electricity. And then there is one that talks about using 2 mini solar panels, 1 motor, and wires. So what that looks like is the We Share Solar has, they have a printout if you want for this. You don't necessarily need to make this printout. Basically what the kids, they get to play, and this mini solar panel and wires and motor look like this. Here's some of the wires, and not all of them, and here's a motor. One helpful thing to do would be to tape something to indicate the RPMs, which way this is spinning, because that's going to matter. But the first task is, can you make the motor run? These are called alligator clips. So if you clip them open, you can clip it onto a metal tooth of the motor, and that's going to be 1 terminal. The solar panel, red's going to be positive, black's going to be negative. These photovoltaic cells do not work inside. They need to be outside with the sun, because the sun actually has real photons. It's going to use to power this. But you're going to essentially hook this up. One useful way to do this is to just clip the alligator teeth onto the other one, and then you would hook the motor up. You can see how to make the motor run. The kids really get to play with this and kind of understand electricity at a basic level from a renewable energy source. How can you make it run faster? You can give the kids multiple solar panels and try and have them hook up to the motor. One trick here is understanding a series versus a parallel circuit. That is a big thing for them to take away, especially with the suitcase. That's how a light switch works. It turns off a certain part of lights. And then another trick is they're going to try and make the motor run backwards. So how can you reverse the polarity? How can you switch around the wires to make this motor run the other way? In their printout, they got some other things that you could use as a talking point. I did print this out for my high school physics class. I did not do this with my 7th grade STEAM class. We ran out of time, but it was more helpful just to have the printout so they could see what the tasks were, and then just to go outside and have fun. That's what this whole activity was about. So once again, We Share Solar follows the 5E learning model by the NGSS. So this is the second E, Explore. So that first E, Engage, was using the solar panels, trying to get you involved in the topic. Now you're going to explore it. They have a link to their handout on their slideshow if you wish. If you do make your own slideshow, if you copy their slides, the formatting is not 1-for-1. It does not come over perfectly, which is all right. Some of the videos, these are helpful. And then it goes to describe what are volts, what are amps, what's power, how do we find this? And a helpful thing to do before you get to this part is maybe go home and have them look at what is the wattage of their microwave, what's the wattage of their gaming system, what's the power it takes to charge their cell phone, what are some of these things, what's the requirement, how do you charge a fridge, how much power does that take? or maybe have the kids look at an energy bill with their guardians, so that way they can kind of see, oh, what's a kilowatt hour? How much does that cost? This right here is going to get into a big analogy of water. Water is a really good analogy for electricity. It's essentially, how do you want this water to flow? And electricity is, how do you want these electrons to flow? They're going to use the analogy of a waterfall. So as you can see right here in the speaker notes, they have things that you could read about these two different waterfalls. So looking at the speaker notes, this is in the Yosemite, the one on the left. It's got roughly a 1,400 foot drop. And this question is asking which one has a higher voltage. The one on the right, the photo on the right, is another waterfall that is much shorter, but the waterfall with the higher drop is going to have more voltage. The waterfall with the shorter drop has less voltage. That's the whole idea of the analogy here. They're going to tie that back into gallons per minute and compared to voltage and amperage. And then if you look at a moving river, like the one on the left, compared to a still river, like the one on the right, this is the current of the water. We're going to call this amperage or amperes. The one on the left has higher amperage than the one on the right. Then they have a picture of the same waterfall in two different time periods of the year. The one on the left, a lot of water is falling in, so they're the same height, they have the same voltage. The one on the left has more current because there's more water flowing through it. The one on the right has less current because there's less water flowing through it. They do provide the same voltage of power. Why does that matter? If you take voltage times current, volts times amps, you get watts. Watts is how we measure power. Typically, energy bill is billed out in kilowatts. So a kilo is 1,000 watts. So 1 kilowatt's going to be 1,000 watts of these. And if you did have the students go home and look at how much energy it takes to do, like, how much energy does it take to run the TV for an hour or to the dishwasher, they can kind of relate some of those real world items to this Solar Suitcase project. This goes over some basic math, which you will have to do if you decide. I think a very valuable tool of the Solar Suitcase project is taking these once they're built, taking them outside and doing the worksheet. This is the part that involves a demonstration. So if you can find some sort of ball and some sort of board and some sort of fulcrum point, like a triangle that the board can balance on, and then if you can find 2 objects or 4 objects, one is definitely smaller than the other, you can do this demonstration of power. So they have a 1/2 liter bottle dropping down on this board, and you can see how high up this mango, the load, goes. What they're going to do here is they're going to drop this 1/2 liter bottle from a much higher point, so much more voltage, and they're going to see how much higher the mango or the load goes. In this demonstration, so objects 3 and 4, if you can find one that is bigger, so a bigger current, and then drop it from the same height you did with the smaller current, and then drop it from the same height of the larger difference, the same voltage, you can see how much more of a bigger current influences the height of the mango going up. This is a very powerful in-person demonstration that kind of helps break up the lecture style of the slideshow here. When you go into the slideshow, they go into how to use the multimeter, and there is another lab you can do with the solar panels. So once you learn how to set up that multimeter, this other printout and this link for this Google Doc came from the slideshow. They show you how to set it up, and you can measure, you can take it outside and you can physically measure the voltage produced by one solar panel, the amperage, and then you can wire it in series. So in series, this is all the old light bulbs before 2010 for Christmas lights. When one breaks, the entire strand's broke. So when they hook up these solar panels in series, they can see the difference in voltage or in amperage. When you hook it up in parallel, so these are your new light bulbs, the incentive in 2010 to buy LED light bulbs, they're hooked up in parallel. So if one breaks, then the rest of them still work. This is a helpful thing to learn how to wire up, and then you can physically see a number when you take this outside. This worksheet is not something I got a chance to do with my physics kids, but we did it in March and April, so weather was not cooperating. I would have done this if I was able to. There's some more graphics on how to wire series and parallel on the slideshow itself, which is helpful. Basically, you're going to have the alligator clips clipped to each other, and you can clip multiple ones to one of them. The water analogy is back for series wiring. This is talking about cylinder and pressure. And then when you have series connection, they go through how to do the math for some of that. And some of the other things that were really helpful, so going back to the curriculum, you'll notice that We Share Solar has taken the time to really go in depth with some PhET simulations. And these PhET simulations were extremely helpful for my high school physics class. I did not get a chance to do this with my 7th grade students just due to time constraints, but for a higher level student in a physics class, the understanding of the Solar Suitcase directly with this PhET simulation was extremely helpful. Looking back on it, you do not need to print this entire packet of 9 pages. This could either be an online document or this could be something that they just work through without having to print it. It's a lot of talking points, so this is a much more low-key day where they are doing a lot more reading rather than interacting with you. So this is what the PhET simulation looks like, and there's a link to it. You can definitely go around and see how they're doing with that, but like I said before, this activity itself is not necessarily as teacher-led. There's a few questions, so if you just want to print the questions out, that would be helpful. Otherwise, if they want to fill them out online, or if you want to strictly keep it to more of an interactive activity rather than documenting some sort of feedback, that works too. This is a series circuit, and the rest of the 9 pages kind of go into what is a source, what is a load, what is a switch. These are common words and terms used by the Solar Suitcase. I actually did this before we built the suitcase itself, so when the kids went into the project, they kind of had an understanding, a very basic understanding of how the suitcase works. This right here is a parallel circuit, so if you're not sure how to wire one yourself on the PhET simulation, there is one right there. And then there's some more in-depth questions, so when the students build this one, they can answer, hey, what happened in this specific question? Just like in this one as well. The second PhET simulation from the We Share Solar curriculum, this one kind of integrates a little bit more of pictures directly from the Solar Suitcase, and now they're going to go into and they're going to try and build their Solar Suitcase on the PhET simulation. It tells you what a charge controller is. This is actually a very informative lesson explaining, like, I have this black box called the charge controller, but what's it actually do? Why is it called a charge controller? What are all these leads? How does that work? In the PhET simulation, they have to go through and they have to build different series of like a series with 1 light bulb, 2 light bulbs. This is no battery. This is a solar panel, a switch, one for 1 light bulb and another switch for another light bulb. And then this is kind of what it looks like. So they overlaid some of the graphics of a solar panel. The kids are building, quote unquote, a solar panel and a battery and a switch, and they overlaid a picture of what that should represent, so that way they can kind of realize that. Once again, I printed this out, but this is 11 pages long. I don't think I would print it out again. I think I would make it a digital document that they could access and work their way through, but it was super helpful. So that ultimately, they're trying to build this. This is how the charge controller works. When it's hooked up to the solar panel, they used a battery just because there's no solar panel option on the PhET simulator. And then they use a switch, but this graphic right here when we went through this FET simulation on a Friday, we came back on a Monday and built the solar suitcases. A lot of the kids are like, oh, I understand kind of where the flow of electricity is going. And then they put a graphic of their classroom set for a solar suitcase.